Good morning everyone, and welcome back to our tutorial on CNC, lathe, programming. I want to discuss face milling with a free shape. For example, the letter T, I prepared raw material with a diameter of 200, zeroed C-axis, and used a 10 millimeter candle cutter. We'll take the contouring of the letter T as an example. To do this, I've already prepared a raw material with a diameter of 200, activated the motors, zeroed the C-axis, and called up a candle cutter that fits the self-centering with a diameter of 10 millimeters. I've set my cutting parameters. At this point, I need to go to the soft keys related to the machining cycle. The machining cycle, which in this case is a contouring. We select the contouring and start entering some data. We want to create a letter that protrudes 10 millimeter from our base. So here we enter 10. For the side excess material, in this case, I want to engrave it, not hollow it out. So I'll set an excess material that's less than the diameter of the cutter. Let's set it to 5. After that, we'll do a few examples. For the radial cutting depth, let's set it to 5, which is half of our grip. For the axial cutting depth, we'll do it in 2 passes. So, half of P, which is also 5. No side excess material, so 100th is fine, 100th is fine, and the feed rate is good. Specifically, I want to work in sync. And I want a safety distance of 5 meters. For the approach type, let's set it to tangent. Then maybe we'll see what changes, and we'll also make the exit tangent. Let's insert our loop. At this point, I'm asked what I want to do. Well, I want to create a freeform shape in the XC plane. I select it, and the Cartesian coordinate plane opens up, where I want to draw a T. As you can see, it can't be modified because the loop already includes the outlining of a face. Starting point. I put 40, 0. We said the base position, Z, is 0. And here I always get confused. I never remember if I need to put the depth. So the depth is 10. If I also need to include the sign, we'll add it, and then we'll evaluate it in the simulation. Okay, now my Cartesian coordinate system opens up, and you can see that. X is 40 and C is 40. Good, they are not diametrical. We are actually working in a Cartesian coordinate plane, where C is vertical, and X is horizontal. When I write 40, it corresponds to 40 real millimeters, in both X and C, measured from the center. Now I want to draw a line to the left, which will be the head of my letter P. So I write left, because I want to go left. Now I want to draw a line to the left, which will be the head of my letter P. So I write left, because I want to go to the left. Final point in X. I'm not putting the length of X, but the final point, so minus 40. I just send it. Okay. Here we have made the head of the T, so the width of our T will be 10 millimeters. Now I'm going to draw a line, and I lower it by saying, go down. it automatically tells me, well then I need a C, area plus 40, so you'll go to 30. Okay, good. I also want to make the stem. Actually, let's make the stem a bit thicker. We'll make it 10 wide. So I go back towards the center and insert another line. Now I'm going to the right. So I'm at minus 40 and I go to minus 10. Okay, sorry, I didn't put the minus. So let's modify that. You see that the minus is missing. I noticed it right away from the graph. Okay, well I also want to make the stem. In fact, the stem, let's make it a little more plump. Let's make it 10 wide. So I go back towards the center. Then I insert another line. I'm now going towards the right. So I'm at minus 40. I'm going to minus 10. Okay, sorry. I didn't put the minus. So let's modify that. You see that the minus is missing. I noticed it right away from the graph. It continues and knows that I at least have the keyboard, which sometimes works and sometimes doesn't. Now I'm going down to make the stem of my T. I'm not going to 0, but I'll go to C40. So I draw a line down. It automatically tells me, well, I need the C, and I write minus 40. I hit send. Okay. You can see that the T is taking shape. The bottom part. We're going to make it slanted, just to show you how to create a slanted line, so it's in line. At this point I say, well, I would like you to go up and to the right. Here it asks me for 3 possible coordinates, the x and the c, or the angle, depending on what I have. I remind you that the angle is read 0, 30, 40, 50, 90, counterclockwise. So x becomes 10 cent and C35, okay. At this point, I don't need the angle. You can see that we've created a slanted line. Here, I want to add a connection. No problem. I add a connection, R3, send. Okay, you see that it doesn't draw it because it doesn't know the direction in which I will move with the next line. The next line I will make goes up to C30, send. Okay, you can see that it has gone back up to the left. Line, X40, send. Okay, here I am. Perfect. Let's close our line. So, up to 40, okay. A few small considerations. In this area, we won't have a sharp edge, but we'll have a radius equal to our milling cutter. So if we want a radius here, or a connection, we need to program it to be larger than the radius of our milling cutter. Otherwise, it gets ignored or gives us an error. Finalize line to 40. Use radius matching cutter. Start and end at X40, C40 to avoid errors. Okay, a few small considerations. One, in this area, we will not have a sharp edge, but we will have a radius equal to our cutter. So if we want a radius here, or a fillet, we must program it greater than the radius of our cutter, otherwise it will be ignored, or give us an error. Another consideration is that if I start from X40, C40, I need to end at X40, C40. Otherwise, we'll generate an error to fully understand this concept. At this point, all I need to say is create. Okay, it created our nice design. Let's simulate and configure the 3D model so that it doesn't run too slowly. Alright, let's directly rotate our axis. As we start the simulation, here we have our T. This line you see is the tangent input and the tangent output. We want to remove it. It's very simple. Normally, this isn't a problem because this whole part gets emptied, so I have to say it caught me off guard. But let's go here. Go to our cycle and tell it to modify. I don't want the tangent input and output anymore. I want them vertical. Enter, modify, and let's go to simulation. Restart, start. Okay, you see that I've assigned the input anyway. Obviously, this type of problem can be eliminated, and now I'll explain how. This line you see is the input, tangent, and the output, tangent. We want to eliminate it. It's very, very simple. Normally this isn't a problem because this whole part gets emptied. So I have to say it indeed caught me off guard. But let's go here. Go to I'll cycle and tell it to actually modify. I don't want the tangent input and output anymore. I want them vertical. Enter, modify, and let's go to simulation, restart, start. Okay, you see that I've assigned the input anyway. Obviously, this type of problem can be eliminated, and now I'll explain how. But first, I wanted to show you how to generate an alert, and this is the way. So, let's go back to our figure, in fact. But first, I wanted to show you how to generate an alert, and this is the way. So, let's go back to our figure. You'll see that we also close the circle of that ugly mark. Let's go back to our figure, which is this one. Figure, okay, modify. So let's imagine what happens when I press these buttons here. When I enable this, we have yellow for the starting point. When I enable this, we have yellow for the first horizontal line we find, and so on. If I go here, it corresponds to 1. To the first line that goes upwards. Let's find this instead. It will correspond to the second line going down that we find relative to my profile. Okay. Anyway, if you don't want to get confused, just click until the line you want to modify turns yellow. Good. I want to modify this one. How do I want to modify it? I want to insert a 3 mm connection. Okay. Good. The drawing looks perfect. Let's create it and see what happens. Simulate. I restart the working area. Wrong. What's the problem? The problem is this. Let's go back to our figure and modify it. So I started programming a point. Okay? 40, 40. You see? By modifying and adding a connection, if you notice, it no longer falls on 40, 40, but on 37, 40. So, for the machine, this is not a closed figure. How do I solve this problem? And at the same time, the issue with the entry marks in the processing. All right, I'll do this. I'm going to modify the starting point. I'm not going to write X40 anymore. I mean, I'll leave X40. Sorry, I'm getting confused here. Okay, modify. I'll leave C40, but I'll set X to 0. Modify. Okay. Then I go to the last line. We inserted the connection. I add a line to the left and set it to X0. Okay. Where did I go wrong? Because I modified it. So let's undo all the changes. We said we would modify the point and set X to 0. Enter. Okay. Sure, because it still has the radius in memory. So, after the radius, I highlight my connection and insert a line to the left that goes to X0 and effectively closes my figure. At this point, I'll start working from here. Create. Okay. Simulate. Restart. Start. Okay. You can see that at this particular point in time I have the entry bevel here, so I'm going to make necessary modifications to the cycle as It was, initially, entering and exiting tangentially with a measurement shorter than my half of t. So, modify, simulate, restart, and start. You can see that we no longer have the entry bevel, because the cutter now enters tangentially. And we also don't have the error anymore, because I started my machining at one point and closed it exactly at the same point. I could have them start from here by basically changing my end point to match my start point, but I would have had trouble getting rid of that little face. But now we want to remove all the material around it. How do we do it? We go into the cycle and not into the figure. We modify it and we increase the excess metal. Now with a moment it's quite difficult to get the exact correct excess material. Let's assume 80, which is the maximum excess material to be removed from X to X. Simulate, restart, and stop. You see the machine starting to work from afar and roughing out everything it needs. I would say that 80 was a good compromise. Okay, now it seems like we're doing something bad, but in the end, T will come out. Next time, let's choose another letter. First pass at a depth of 5 mm, second pass. Another 5 mm, so let's remember that when we draw a free shape, both C and X. These are the coordinates of the actual distance from the center of the piece, so basically radial dimensions. Let's remember that the shape needs to be closed. And regarding the entry, if we need to create a shape like this, we can set it tangentially, directly, or as an arc. If we need to create a recessed shape like the one we saw, initially we have to be careful, otherwise it will leave us with an entry bevel, which is that ugly thing we saw before. We put the wheel, we turn it, and there you have your T. Here you need to get the hang of how to draw it, because the first few times you might have 4 holes and you'll find yourself with those 4 scattered holes. Then you'll just need to rotate one of the 2 shapes. It's really about getting some practice. At this point, still working on the same shape, you can do a finishing touch, you can add a chamfer, whatever you want. There it's a bit of a matter of getting used to it. At this point, always on the same figure, you can make a finish, you can make a chamfer, whatever you want. That's why, be careful. Often it makes sense when you convert this shape into code. You see, when you write modify, you modify it and say create. Sometimes it's better to create it as a subprogram so that you can do the roughing cycle and call the subprogram, then the finishing cycle and call the subprogram again, because the profile is the same. The chamfering cycle will also call the subprogram because the cycle is the same. Let's try an example. Modify, create, subprogram creation, 002. Okay, you see that it automatically called a subprogram. If we do list, we can find it here. Now if I want to do my finishing operation, I'll choose another end mill. Let's make it a different diameter, keeping the parameters the same. Let's go to Tool, Correction. I'm using End. Mill number 26. Let's use number 27 and set the diameter to 2, so a small one. Let's see if it's an end mill. Yes, it's an end mill. Close. What am I doing here? I have insert components like 0, 7, and 27, and I'm inserting my new instrument or tool. And then I'm going to add a final finishing cycle. So it's always a contouring cycle. But this time I want to do a side finishing operation. So the excess metal material just needs to be less than the cutting tool. So 1 over metal will be just fine, which we'll have on the side at 0.01. In this process, such as in this case, for example, specifically in this scenario, it was, but let's put 0.1 since it doesn't know because these finishing cycle passes aren't linked together. Finishing 1 feed rate is 5.5 and axial approach is 50. Work in accordance with safety distance 5 mm. Entrance. We do it vertical 5. We make the exit vertical and 5 mm of safety distance. We insert under program 002. Nice, it's definitely ready. Simulate, start from here. The convenience of the subprogram is that I could have indeed increased the cutter radius a bit, so we wouldn't have to wait. See, I didn't link the roughing cutter's radius to the finishing cutter's radius at the point where we have the shank of the T where we will meet the cutter's radius. So, for actual machining, this could create a little problem. That subprogram discussion obviously also applies to traditional shapes. So, for squares, hexagons, and ovals, you just create one and then set up the cycle, calling the subprogram each time, and you'll see that we have it. I must have had the same color. Anyway, we finished it. Now let's rotate it so we can see the work done clearly. Alright, I've wrapped this up. Here, let's rotate it so we can see the work done clearly. Alright, I've wrapped this up. This is the most important part. It's important, in my opinion, because often we find ourselves creating shapes that aren't traditional. Think of a cam or a design feature that's not mechanical, which requires a finish that doesn't correspond to a standard geometric shape. With this, you can create everything from standard geometric shapes to the letter T to a cam, and so on. And be careful, because here we don't have what I call mushroom mills in the graphics. You see, if we go here, we only have, you see, drills, chamfers, candle mills, round mills, taps, reamers, and bar mills, but we don't have anything else. With a mill shaped like a mushroom, you can also work on the back, depending on the length of the mill itself, so inside the solid material. And this can definitely be interesting. Well, with that, I've finished today's discussion. I hope it was of interest to you. If you liked it, as always, give it a thumbs up, subscribe to the channel, and share it on your social media. If you didn't like it, just pretend you didn't see it. Thank you, and see you next time.